is how it looks like. This is the system we have in Pécs at the biophysics department. Actually, this is the only system in Hungary. I mean, this type of 20-second transit absorption spectrometer. Of course, we have nicer, faster, or stronger lasers in the country, but this is the only system of this type. So now this is what happens here. I will mention a little bit later. This is the laser beam coming out, and we are using second atomic generation. I will mention later, and this goes to the sample, and this will be the pump beam, which will be a blue beam, and that goes to the sample as well. And this is what we see. Now, this is what we can see on the CCD. The CCD is our detector. So this is the abbreviation stands for charge coupled detector. So this is the detector. And what we are measuring here, this is basically, we have a 1,600 pixels, and we are measuring the light intensity on these pixels. This is what we can see primarily on the detector, and we have to convert this information to wavelengths and numbers. And this is what we can see here. This is the so-called white light continuum. This is important, the white light continuum, because this is our probe, the white light continuum. This is like the lamp, the bulb in the normal absorption spectrometer. If you have this table-sized spectrometer, when you measure just the absorption, you have a lamp. Actually, you have two tungsten lamp and a deuterium lamp inside. So this is what you have inside. You turn it on, and you have the lamp, and this lamp, this beam goes through the sample, and you can measure what was absorbed. Now, the lamp is this white light continuum. This is very interesting because this is a nonlinear phenomenon. And what happens here that you hit a calcium fluoride crystal with actually a low intensity beam, laser beam, what we have here, and this will generate continuum. And actually we can use a lot of different materials to generate continuum, because if you have power enough, you almost always generate continuum. Actually, this is quite a disadvantage sometimes. So if you hit your pulse in the water, you will have continuum. If you just direct your beam on the mirror, you will have continuum. So it's easy to make continuum. It's not so easy to make a nice continuum, where you have photons enough in the UV region as well. So this is what happens here. This is a special one, this is calcium fluoride crystal, and we hit it. And the calcium fluoride is good, and it's loved because we have enough photons in the UV region as well, and that's what we need. And also, sapphire crystal is also a good one for generating white light continuum, but in that case, the continuum starts with 500 nanometers. Not to have damages on the crystal, we have to move the crystal. This is the only disadvantage, that we have to solve somehow the movement of the crystal in order to avoid the damages. Now what happens here? If you, actually this is just a so-called octahedral porphyrin. This is an interesting chromophore, what we have in hemoglobin or myoglobin as well. And it has an interesting absorption spectrum. And if you put a porphyrin sample in the beam of this light, white light, you will see this pattern on the CCD. And basically what you see here, you can see which region is absorbed. It's absorbed very well here and here. It's not absorbed in this region, whatever. And this is the transient absorption spectrum, what you can see from this porphyrin sample. Why I'm mentioning this? When I'm mentioning porphyrin, because this is a good material. It's a test material for us, because it has a very, very good absorption at 400, and actually it doesn't decay on our time scale. Our time scale is decided by the length of the delay stage, so we can measure up to 3 nanoseconds. And the good thing that the porphyrin doesn't decay after excitation on this 3 nanoseconds. This means that we have to arrange and we have to optimize the system, and we have to have the our system, and so this is the control of the software. And maybe I just show you rather how does the measurement happens. And I made a small movie. Okay. The thing is that I checked before. So this is the porphyrin I just mentioned, and this is the transient absorption spectrum. What we are reporting, what we can have at the beginning. This is called excited state absorption, and we are setting the measurement here on these panels, and this is the so-called tuning panel. Now I just stopped I set back the delay stage to time 0 when the pulse and of the probe pulse and the pump pulse, they are coming at the same time. And hopefully I started the measurement, and we'll see immediately the measurement starting. This is just from the previous measurement, the last spectrum. It's a little bit noisy, but it's there, so you can see. So this is the primary information we can get from our measurement. I will enlarge here the scale because porphyrin has a huge signal actually. So this is the transient absorption spectrum what we are measuring. And of course at the same time we are not measuring only, so we are measuring the spectrum at many different time steps. Actually here maybe you can see that we have, I don't know, 100 something, 38 time steps or so. So it should decay in some cases. And now we are measuring the kinetics here. So I will set here the wavelengths to 430 or so. So we can measure the kinetics at 430 nanometers. And as I mentioned, so I set there 430. And as I mentioned that we shouldn't see a decay with the porphyrin. So this is the kinetics at a given wavelength. This is what we are measuring. And you can see that, there is no decay. Of course, this is fluctuating. This is the noise of the sample. That's why we have to make a long averaging, so repeating the measurement many times. But you can see that all in all, it will be flat, so it's not decaying. So basically, the system is well aligned. More or less, you will see in the next step that it goes back, but that will on the line. Okay, so this is how our software works, and so I want to show you here that of course we can measure the kinetics, and this is the kinetics measured oxidized FAD, and we also got back the so-called 9 picosecond phase, close to 9 picosecond phase with the FAD. And this is how it looks like in transient absorption data. Now, the question, of course, the big question, how we can analyze the data. Data analysis is very important. I will jump back on the other software here. So somehow it's hidden behind it. And I wrote some samples, different samples. So this is a software called Glotaran, and it's not a Nordic god or something like that. It sounds like, but it's something. It's global and target analysis. And the global analysis and target analysis, so it's partly on my talk today because it needs more time. But basically, so this software was made by a colleague of mine, and basically this is the best software in the field at the moment to analyze transient data, let's say fluorescent data or also absorption data. What we can see here, this was just Flavian mononucleotide FMN, and this is basically an output of our measurement. This is what you can see at the end of the measurement. This is the time axis, and this was the wavelength axis. So if you just put your mark on, let's say this line, see the spectrum at different times here. Actually, it's an interesting thing, and it takes a long time to explain, but it's good to know about this. When you see this one in the beginning, when the probe pass arrives very closely in time to the pump pass, you can see this noise. Actually, this is how the light is dispersing in time. You will see the light is traveling, and at the end of the day, you will see the signal. So this is how it was traveling. You can see your resolution. You can check your resolution actually in this way. This is called the so-called coherent noise. Now, so this is how you analyze your data. This is a typical transient absorption spectrum. And what else you can see here? Let's say on this one. Yeah, let's say this one. This is my protein. What I had, and you can see the decay at this certain wavelengths. And what we can see, we can analyze. And as I mentioned, we have no time to go into detail of global analysis, but I did before, so we can have an overview. And what you can find from this analysis that you have a couple of different species. So in this system, in this case of this special protein, you have different species with decaying with different time constants, and these are the spectrum associated to these time constants. It's very interesting. So this is what you have at the end of transient absorption measurement. Okay, so let's move very, very fast to the rest. This was data analysis. Transient infrared absorption spectroscopy. This is very, very similar to the visible transient absorption visible spectroscopy, visible absorption spectroscopy. Just we are using infrared lasers for this one. And this is not easy, so you cannot do it at every corner. This is the Rutherford Appleton Laboratory in UK, very close to Oxford. And this is Diamond, maybe you have heard about. This is a synchrotron, what we are not using. And this is our Fortress. This is the central laser facility. And we have many, many lasers here. This is actually this user community. That was a couple of years ago. These are the guys who are using this laser system. So what happens here? So you have your pump probe scheme here as well. You are pumping your system and you are probing it. And you are changing the difference between the pump and the probe, and that's why that's how you are measuring the kinetics. This is basically the very same idea, and this is how it works. This is the system, and this is my colleagues working on the system. We have a couple of amplifiers here, so we have no time actually today to go into the details how many different types of amplifiers we can use. We have a couple of them. This is just how it looks like. This is very interesting because I haven't shown you, but I will show you in a moment how the sample holder, the cell looks like in the case of visible transient absorption. So this is even more specialized. We have so-called Herrick cells here. These are typical infrared cells with a 50 micron spacer, which means that you can use a small amount of sample, but it should be very high concentration because the thickness of the sample is so small. So what you are doing here, exciting with this blue beam, and you are probing with this infrared beam, which one is here, this purple one. And this is just the design, it's not so important. This is the primary data, this is what we get. This is basically transmission. So we have our infrared beam. What we are using here, these are also detectors, these are pixels, and we measure the transmission. What happens say we can have a different absorption of the infrared beam. Now if you make a different spectrum, what you will have? You will have here these two so-called ground state bleaching, and you will have this excited state absorption. Now, of course, I haven't mentioned, so why is this? So you can imagine easily that this is your ground state. If you excited your ground state, your molecules will be an excited state. In this case, here, you will have more light. More light will go through the sample because the population is in excited state, so they will not absorb it. That's why you will have this negative peaks here. And this is what happens here. And now what we are collecting at these different spectra, different time scales, and this is a typical transient infrared spectra we are measuring. And these are some typical measurements. This is FAD, normal oxidized FAD, a nice, beautiful measurement. And the ground state bleach, you can see the decay of this close state FAD, so close to 90%. These are just details what we did, and I will jump this one because it's too many information for our paper. What I want to show you, just the data here, what I wrote in from the transient infrared, which is interesting. This was a transient infrared measurement. What I want to show you here, you will see a peak rising as the time is going on. You will see a peak rising, and this is very interesting. A flavian mononucleotide can form a so-called triplet state. And this is what you can see here. This is the marker for this triplet state, and you can identify this triplet state forming. So you can calculate, actually measuring how fast is this triplet state is formed and how fast it's decaying back. So this is a nice thing. So we did some basic photochemistry as well. Okay, so we don't have too much time, so I'm speeding up. Let's talk about fluorescence upconversion and basically transient fluorescence spectroscopy. So these will be two methods, what I will show you here. Two methods to measure fluorescence lifetime on a very, very short time scale. If you go on the other side of the river again, maybe you will visit my colleague Asa Groma, and he has a nice system for fluorescence spectroscopy. He can measure the time-correlated singular photon counting. He can measure the fluorescence lifetime in the nanosecond range, and he also has this fluorescence upconversion technique combined in the same system. So what happens here? It happens that we have some crystals which are so-called nonlinear crystals, and in these nonlinear crystals we can have phenomena called frequency mixing. Frequency mixing is very easy. It's just a description of the conservation of energy and the conservation of the momentum. So at the same time, they have to be true at the same time. What happens here? The important thing, due to the frequency mixing, you can double your frequency if you have a proper crystal in a proper angle. And this is what we are doing, generate almost all the time. We have a crystal so-called BBO. This is a barium borate crystal, and you shine the light. I mean, you have a short pass, a femtosecond pass of 800. At the end of the day, you will have a 400 nanometer pass coming down from this crystal. So this is the second harmonic generation or frequency doubling, and this is very useful because many of the proteins or many of the samples we are measuring, they can be excited 400 nanometers, which is very cool. Also in microscopy, you will see that huge range of dyes can be excited at 400. Now, I won't show you all these categories. this is just another case of frequency mixing when we can actually tune the color of the beam. We have also in our lab, we are doing this, which is called non-collinear optical amplification. This is a little bit trickier. We are using two beams here. We are generating white light in this sapphire crystal, and we are directing in this video. We are generating a blue beam, and we are directing also in the second video, and we will have a new frequency or a new wavelength, as you can see here. What we can actually tune. Basically, the company who is delivering the huge laser in the X-ray laser facility here in Szeged, they were the first, how can I say, the best company providing this computer directed or computerized OPA systems, so they are the best on the field. Light conversion, they are called. Now, this is different type of frequency mixing. Now, this is how it looks, typical up conversion system. You don't have to understand every step of it, but what happens that we have a Zeiss-Sapphire oscillator. So this is what we are using. We are using the same oscillator and the same beam basically for the excitation. Just we are using here somewhere video here, barium boron crystal. So we have a blue light, and we are directing this blue light on this sample, and we are exciting. We are having fluorescence from this. What we are doing, we are collecting the fluorescence here, and we are directing this fluorescence on the second nonlinear crystal, second BBO. And we are directing also a part of the original beam from the titanium sapphire laser. And when it's phase meshed, so when the energy conservation and the momentum conservation happens at the same time, I mean it's optimized, we will have an outcoming beam. And basically, we have a stage also here, and changing the stage, changing the time difference between the pulse and the fluorescence, we will measure a fluorescence decay as well. The only problem here, that here you are set to a certain angle, and the angle will define at what kind of fluorescence you can detect. So you will have an angle here for, I don't know, 460 nanometer fluorescence. You will have a different angle for 470 nanometer. So that's a disadvantage of this system and this technique, that you have to arrange all the time the angle of the crystal if you want to detect different type of fluorescence emission. But it's a good system. This is what we use at UEA, and this is our cell somewhere. Yeah, it's here, and actually we are collecting, this is a Cassegrain objective, we are collecting the fluorescence with this objective. I will show you another picture of this. Before jumping there, I want to show you another thing. Sample holders are very important actually in the ultrafast spectroscopy, and this is our sample holder. Actually, you can have to rotate the picture, something like that. I will show you again. You have to move your sample in order to avoid damaging of the sample, because this beam can damage your sample, and you have to rotate it now. So this is something went wrong, slow down, but doesn't matter. So many times it's very important to flow the sample, to rotate the sample. So it's also a technical detail which might seem minor, but it's very important. Now, what can we measure? We can measure basically the same thing. We can measure fluorescence decay in this very short time range. What we have, these were actually blood domain proteins and different mutants we measured a couple of years ago, but you can see again that we are in the ultra-fast regime. And these were the numbers we measured. Now, I jumped through this up conversion because you might see it at the Biological Research Center. And also jumped because to this one because this is our baby because we built this system in France at École Polytechnique in the last couple of years, and we have a chapter in this book about this gated fluorescence spectroscopy. If someone is really interested, I can send the PDF of from this book, the chapter. Now, what happens here? It's very interesting. This is based on optical Kerr effect, and actually we have an electric Kerr effect as well. The Pockels works in that way. If you have a special crystal, in the case of electric Kerr effect, if you apply a high voltage, I mean 3,000, 4,000 volts, it will introduce a polarization change in the crystal. So this happens also with in this case, just we are using not a high power, but we are using the laser pulse. So we are hitting a crystal with a huge laser pulse, and due to the nonlinear part of the refractive index, we will introduce a change in the polarization, and that is critical here, as you will see. Now, what happens? How the system works? It might seem complicated, but it's very simple. The idea is simple, to make it's not so simple. So you have, basically this is your laser, the red one, this is your laser, what you are using for the whole thing. And it comes from this direction, basically. So what we are doing, one part of the laser beam, let's say 50% goes to the left. We have this nonlinear crystal, the VVO, and we are generating a 400 nanometer beam, which is used to excite our sample, which is cool. And the sample will produce some fluorescence. This is the fluorescence, and the fluorescence is collected, but by these two objectives, which are called Cassegrain objectives. They are here. So basically, we are using it to first to make it parallel to fluorescence, and after that to focus down to our Kerr material. What is very important here that we have a polarizer here, and we have another polarizer here, B2 here. And these two polarizers are cross-polarized. So in a normal case, you have no fluorescent light coming out after this lens, and we have this is a CCD, because they are cross-polarized. We have light only in that case if a laser beam or laser pulse arrives on this Kerr setup and introduces a small change in the polarization, and this small change of polarization lets through the second polarizer a part of the fluorescent beam. This is cool. And now what you are doing, you are controlling the time when this pulse arrives to this Kerr material with this delay stage. This is the same idea. You are moving delay stage, so the beam or the gating beam will come earlier or later. So we are also collecting fluorescence decay. So this is how it looks like. So this is the sample holder. We are moving it, we are cooling it, and we are collecting these other Cassegrain objectives. We are collecting it, and I have made a picture of the CCD. Now, we have a trick here because actually it shows that we are directing this red beam on this Cassegrain objective, and it focuses the red beam on the Kerr material. So I glued this small mirror, actually, mirror holder and the mirror in the middle of the Cassegrain objective. This is what is needed to make to focus down the Kerr material. Now the Kerr material is very important. It can be almost everything, but we have to think what to use. You can see that we have here a couple of different materials. We have something, a solvent which is called CS2. This is the most loved Kerr material in the field. It smells very badly, but it's a very good Kerr material because if you introduce your beam, it will introduce a huge polarization effect, and you will have a lot of light going through. The problem with the CS2, the relaxation of this liquid back to the normal state takes in 1 picosecond. This means that if you have a process faster than a picosecond, you won't be able to catch it. You understand why? Because your gate is still open when your next thing is coming. So benzene, it's something in between. This is better. As you can see that the relaxation time of benzene is 500 femtoseconds. So this is faster. This is what we do at the beginning. Usually we start with benzene because the resolution is quite good already, but still you have a good intensity. But if you want to measure something very, very fast, you have to use Suprasil for this reason, which has a very fast relaxation, 100 femtoseconds, but you will have far less light, and that's a problem, of course. Now, okay, so this is just some measurements I did on my proteins, and this is photolyze, of course, and this is so-called antenna in the photolyze. Basically, what I want to show you here, this is the picture what you get after a normal corrugated fluorescence measurement. The advantage of this technique compared to the conversion is huge. You can see it here, because you don't have to set your crystal every time to have different wavelengths. Basically, you will get the whole spectrum in the same time. In one shot, you will have the whole spectrum. This is what you can see, that we have our measurement is from 400 or so up to 800. So this is the whole spectrum in one shot. So this is very, very cool, I would say. And I will show you a primary data in this picture. So I will go back to Glotaran. We can analyze fluorescence of conversion also in Glotaran. Not this one. Sorry, I forgot to open it. Okay, so we have to jump back to the presentation. I forgot to open it, and I won't spend time to find the file. Just what I wanted to show you, which is very interesting, at least for me. Yeah. Please. Yeah. What is very interesting that what you can see here at the left side. Can you guess what is it? This small peak. Because this is your fluorescence, so this is easy to measure, and you can see the spectra. It is quite fast, and what you are measuring, you measure the spectra at different time steps. This small something on the left side, if you make the calculation, this is your Raman peak, and this is very nice that you can measure just the Raman peak, the Raman scattering. I think this is cool, and this is what you can see on your left hand. And what I wanted to show you, that as we are changing the time setting, you can see the Raman peak appearing and disappearing, and I would say this is very cool because you can see that on this very short time, your Raman peak arriving and disappearing. What we have measured here, this is basically the photolyze, and we measure, you can see that indeed, again, this is ultra fast, so it's a very, very short process. So the fluorescence, it's also very, very, happens in a very short time scale. So now, what we have here, I just collected our measurements, what we did on different mutants. So we have the wild type photolyze, we made a couple of mutant, and this is what we measured. And you can see on the time scale here that indeed we can have some very fast processes in these proteins. So this is basically the case in less than 5 picoseconds. So I would say that this is a very fast one. And you can see that we can measure longer processes questions. So acknowledgement goes to my colleagues in the different departments where I was working, where I have collaborations to University of East Anglia, to the Stony Brook University in New York, and of course to the Polytechnic, and to my colleagues in the biophysics department. So these are just some extra slides. But if you have some questions, please ask me the questions, and I'm trying to answer them.
Sorry, could you please show the program that your colleagues did? The programs and
Of course, but that's not my colleagues, it's ours.
okay.
The software, you mean the data analysis?
And the first the data you showed us.
Yeah, sure. This one? The details of the software?
Yeah.
Okay, I can enlarge it for you. So we are using many tricks here with this software. We can do a 3D analysis, a 3D filtering. You can go to Glotara. If you type in glotara.org, you can download it and you can have the description for the how to install it. It's very easy. Basically, it's easy to install. If you have problems, send me an email. I can help you with actually. And he was enlarging the data sets we can use with this software.
And could you open it?
Open? Yeah. You mean the website?
No, not website, but
The software itself? Yeah.
Yeah, and with the graphics.